All right, hello class. Welcome to lecture 21, where we're going to continue our discussion started last lecture, in lecture 20, on how we approximate the rate at which a rare event happens. You can picture in your mind a protein unfolding, a set of reactants going to products, or even a phase like liquid water transitioning to ice. All of these dynamical events are dictated fundamentally by the same sort of physical processes, namely the rare fluctuation that takes that system through a bottleneck, through a transition state, and allows it then to carry on to its eventual outcome. So rare events and reaction rates. So the picture we have in our mind, just to sketch it back out and remind you kind of what we talked about last lecture, was to envision that we have some system whose progress we can monitor with this variable Q, a so-called reaction coordinate. And which exhibits metastability. So there is a basin, call it A, that is separated from a basin, call it B, by the existence of a barrier whose location will denote Q star. If there exists a barrier between two states, A and B will both have a finite lifetime. If you prepared the system in A, you would have to wait a while relative to some characteristic relaxation time, call it tau mole, within that basin, to see the reactive event A going to B. So reactive events, rare events, reactions in general, are characterized by a separation of timescales between a local equilibration within some basin, A or B, and the rate by which that system then transitions between the two states. So for a system evolving within a thermal equilibrium, so imagine that whatever this Q is some coordinate that is fluctuating through its contact with a bath or through its evolution due to Newton's equations. So it's a dynamical variable which, left on its own, would trace out a thermal or Boltzmann distribution. And in such a case, it should make intuitive sense, given what we've done in the class thus far, that the rate, the characteristic number that specifies this dynamical event, in this case, 1 over the rate is the characteristic time for seeing the transition between A and B. Given what we've talked about in the class, it should make sense that this rate, this macroscopic parameter you can measure in a chemical kinetics study, for example, should be related to intrinsic fluctuations that the system undergoes in the absence of any perturbation. Here, one can view the study of reactive events as a kind of perturbation that is analogous to the sorts of things we thought about in our Gaussian field theory, namely it's a conditioning that generates a slightly perturbed ensemble of trajectories. In this case, the rate is equal to a specific sort of conditioning, the condition that I start in A as dictated by some indicator function HA, which is equal to 1 if Q is in A and 0 else. when I average that with another factor and also divide by its average, that imposes a conditioning. So I read this equation as it's evolving as given I start in HA, starting because I've noted the time at 0 in both of those HAs. The rate then is given by the correlation between being in HA at time 0 and then being at HB at time t later, where HB is defined as the complement of HA, so it picks out those configurations as delineated by Q that belong to the B basin and is non-intersecting with the A basin. The rate of change of this object, referred to as the side-side correlation function, is then exactly equal to the rate. So the equilibrium fluctuations that transition a system from A to B encode what the rate of that process is. And this is true if you look back at the last lecture, under pretty mild assumptions that there are metastable states, and so the attempts by which I try to go between A and B are uncorrelated and thus follow some Poisson statistics. So this is an exact expression for the rate, given those assumptions of Poisson statistics, and there are a number of ways to rewrite it, one of which we motivated was to look not at the joint probability or the conditional probability of being in B at a time t later, but rather by inserting that derivative and acting on those correlation functions, we could rewrite this as a different conditioning Q dot here is the flux. This subscript Q star is conditioning to start now not in the A basin, write that more cleanly. So I can rewrite the rate as the flux at time 0, given I start at the top of the barrier. So the flux at the top of the barrier, provided a couple factors, provided I end up in state B at a time t. And this is made possible by the fact that I can bring that system to the top of the barrier just by knowing the relative probabilities of starting in A and getting up to Q star. So another way to think about the rate is the probability to get to this bottleneck state, to get up to see a thermal fluctuation that takes you to Q star, and then multiplying that probability by the flux over that dividing surface, that plane of Q, and imposing a conditioning that that flux brings me eventually to the reactant state. That conditioning is important because it could very well be, in a complicated system, that an initial flux that points me in the direction of B gets turned around by some other degree of freedom not being represented in Q, like a coupling to the bath or some other internal degree of freedom that this molecule is experiencing. Additionally, the opposite could also be true. I could start in the wrong direction and through fluctuations end up committing to B. And so that conditioning allows us to correct for those things. And those are exactly the features that are missed when we make the transition state theory estimate of the rate, which is to completely ignore all of those dynamics at the top of the barrier. So transition state theory just evaluates the 0 time limit of that correlation function, assuming that all trajectories that are pointed in the direction of increasing B, so the flux would take me to B instantaneously, that all of those eventually commit, and that none that are pointed in the wrong way turn around. That, of course, is an approximation, and it turns out that that's an approximation which leads to a variational bound, namely the exact rate is given by the transition state theory rate times a factor, the so-called transmission coefficient, which is less than or equal to 1 and accounts for all of those recrossing events that occur at the top of the barrier. These sorts of events here that, while I initially am pointed in the right direction, turn me around, or maybe events that point me in the wrong direction to start with, but would carry me over to eventually react. Both of those suppress, the neglection of both of those suppress the rate over its actual value, and thus leading to kappa being something strictly less than or equal to 1. Okay, so that's where we've been. So we derived transition state theory. We even worked it out explicitly for a harmonic system. Today, what I want to focus on are a couple different theories for understanding what goes into this transmission coefficient, approximations for treating the dynamics at the top of the barrier. And we're going to do two, so-called Kramer's theory, which essentially models the dynamics at the top of the barrier with an overdamped Langevin equation, imagining that there is diffusion in some degree of freedom that dictates whether or not you eventually commit to the B basin or not. Or in the opposite limit, we'll consider so-called Grota-Heinz theory, which assumes that the reaction occurs quickly enough that the other degrees of freedom are not Markovian, so that they take some time to catch up to that fleeting reaction as it's occurring. And Grota-Heinz theory then models the dynamics at the top of the barrier with a generalized Langevin equation. Okay, so that's where we're going. We'll do those two calculations, get explicit values for explicit dependencies of kappa on parameters. And it's important to anticipate, I think, what we should expect kappa to depend on. So transition state theory is notable in that it depends only on equilibrium quantities. I look at the average flux as given by thermal fluctuations in Q. And then the probability, which is Boltzmann distributed in an equilibrium system, of getting to the top of the barrier relative to the probability of being in the A basin. So those are all static quantities. There are no dynamical variables. There's no sense of what the dynamics are that evolve the system over the barrier. And that's because we've taken the zero limit. So we've taken a static limit. So what we should expect is that variables that encode some of the dynamical behavior, like what the diffusion constants are, what the frictions they're moving through the system with are, those should start entering into corrections through this transmission coefficient. Okay, so let's start with Cramer's theory. So again, this will be a theory for predicting kappa, which in general has a time dependence. So what we want is its steady state value. And we can define kappa as a ratio of a time-dependent rate divided by this zero value, the transition state theory estimate. This kappa should start at 1, and over times associated with tau mole should plateau in general to some constant value. When what will enter into the macroscopic rate constant is that plateau. So let's first assume that we are in a high friction limit. So that the particle going between A and B is overdamped, and whose motion is well described by an overdamped Langevin equation of the form gamma q dot is equal to the gradient of this free energy plus a random noise, where, as usual, the average of that random noise is 0, and it is correlated in a way that encodes the fluctuation dissipation theorem. Now, in general, if omega is a free energy, this is the potential of mean force, or the mean force that results upon moving in Q. If omega really is a potential energy, then it's just a typical force. It's just what you would normally put into Newton's equations of motion. But if this is a system that has many degrees of freedom, I have to integrate out those degrees of freedom. And it's the reversible work surface then that results in this omega. Okay, so we know that provided this overdamped equation of motion, that one way to express that is the stochastic equation of motion written here. An alternative would be through the Smolakowski equation. So I could write down the time-dependent probability of seeing Q at some time t. And if you flip back through our notes, one way of writing that, which is particularly useful for the calculation we'll do now, is like this. So if you unwrap that, take those partial derivatives, you would find the usual sum of convective and diffusive pieces. This expresses it in a means that will be useful, especially when we note that as a continuity equation, this Smolakowski equation takes the form of minus the gradient of a flux in Q, which is in principle time dependent. So how can we use this Smolakowski equation to compute the rate? So the way we'll set up this calculation, the way Kramer set up that calculation way back in the early part of the 1900s, is to assume that we have a source of probability in basin A, and a sink of probability in basin B, such that there will be a flux by continuously put in particles or probability in A and take them out in B. I will drive a current. That current is a probability current. We've just denoted J. And in the steady state, that J will be the probability of being in A times the rate to go between A and B. So by computing that flux, we will be able to infer exactly what the rate is. So this turns a transient problem of a rare barrier crossing into a steady state problem, which is again valid in the limit that there is a strong separation of timescales between local relaxation and reaction. Okay, so our flux can be written by definition as minus kBt over gamma. We look up here, so that was a constant that can go inside that first derivative. I have a factor of the free energy, and I have a partial derivative with respect to Q, the inverted free energy times the probability of Q. And now I will drop its time dependence because I'm going to ask explicitly for the steady state flux, so the time independent flux. So I've turned this dynamical problem into a simple boundary value problem. I have boundaries in A and B that will determine that flux. And this is a first order differential equation that I'll have to manipulate in order to solve for that flux. So to do that, let's instead try to solve first for the probability distribution that results in that steady state. So that's rewriting the above equation, solving for P of Q. So I can bring the J and KBT, or the KBT and gamma, over the left-hand side. I can bring that factor of e to the minus omega Q and an integral from Q. I could choose the boundaries that I want, consistent with the prescribed boundary conditions. Like so. That's just rewriting that above equation, solving for the steady state density. Now note, this is made possible because at steady state, the flux is independent of Q. It's just a number. And that's because at steady state, the flux must be equal at all values of Q. Otherwise, I would build up or deplete probability at an individual value of Q. So from this expression, we can also denote what we mean by P of A as an integral from -infinity to Q star. That's the basin A of P of Q, which through our definition for what P of Q is, this integral equation, we have J, again a constant, kBt over gamma times an integral from -infinity to Q star dq e to the minus beta omega of Q, and another integral from Q to infinity dq prime e to the beta omega of Q prime. Now look at this. This is quite nice. We've got a relationship between P of A and our flux J. That's exactly the relationship we need in order to determine the rate. The rate, rearranging this expression, is just J divided by P of A. We have that here, inverted. This is then equal to J over the rate, or the rate to go from A to B is kBt over gamma, and two integrals, an integral from -infinity to Q star. This sums up the probability at steady state in A, and the integral from Q to infinity dq prime e to the beta omega Q prime. That's essentially given us, weighted by kBt over gamma, the flux that takes that probability in A over the barrier. So it's a double integral over a Boltzmann distribution. And what we found, even without being able to evaluate those integrals, is that the rate now has a dynamical dependence. It depends explicitly on the friction. In fact, it goes inversely proportional to the friction. This should not be all that surprising. What we've done is we've taken a system evolving on some potential or some free energy and insisted that the dynamics are overdamped. So the dynamics that evolve at the top of the barrier are diffusive dynamics, and kBt over gamma is the diffusion constant. In the limit that gamma was infinitely large, there would be no dynamics at the top of the barrier. The particle couldn't go anywhere. So gamma directly modulates the flux over the top of that barrier. And in this overdamped limit, it does so proportionally to 1 over gamma. We can get an explicit equation by using the same sort of approximation we did at the end of last lecture. We can assume that the basin A and its barrier are local harmonic functions. So there's some offset delta omega and an upside down parabola minus beta m, some frequency squared, q less q star squared. For this parabola, it would have some positive curvature, beta there, m omega squared, q less some qa squared, divided by 2, divided by 2. So those will then be Gaussian integrals that we can do. So the first integral we would need is the integral over the A region. Approximating it quadratically. Like so. We can make an assumption, let's give that omega naught. If q star here is sufficiently far away, or this parabola is sufficiently stiff, that we can send this integral to infinity and not miss much of that integral, because it's exponentially damped as I move q away from qa. So that would be approximately just a regular old Gaussian integral whose evaluation we know how to do, giving me factors of 2 pi beta m omega naught squared. The second integral has the exact same sort of form. Again, making the same sort of assumptions that the majority of that integral is dominated. Let's go ahead and put in the explicit form of, so we have this constant, and then we have minus the mass of the particle, some barrier frequency, q less q star squared divided by 2. If the majority of that integral is dictated by small departures away from q star in q, we can send this q to minus infinity, giving us another Gaussian integral, another factor of 2 pi beta m, a different frequency, square root, and a constant shift factor for the height of that barrier. So we've just done the two integrals that enter into this rate expression, so we can put that together. We get KAB is equal to m omega naught omega b over 2 pi gamma. The factors of kbt cancel. And then I have e to the minus beta delta omega, implying, if you compare that to the result we got previously from our locally parabolic assumption, here kappa is m omega b divided by gamma. So the flux, or the correction, the recrossing, essentially is telling you that it depends both on the shape of the barrier as well as the rate of change in the position of that diffusive dynamics at the top of that barrier. which should make sense. The random walk does fill a force as it's moving over the course of the barrier that depends on its curvature. And in the limit that that frequency is really small, so the barrier, the top of the barrier is very broad, I will have a much larger or longer random walk that moves around that barrier before eventually committing to B. This results of a limiting form of kappa in the overdamped limit is known as the spatial diffusion limit in reaction rate theory. It says that in addition to waiting for a rare fluctuation that brings you to the top of the barrier, the eventual commitment of the system to the B basin is gated by a slow random walk at the top of that barrier. So it's dominated by the motion over the barrier, which could be slow if you're moving in a very viscous medium. There is an alternative limit. Imagine that one does not wait for motion in this highly viscous medium to let the system fall down the hill and commit to B, as is reasonable to expect in the overdamped limit. Imagine we are in the alternative limit where motion is very underdamped. Remember, damping really refers to the ability of the bath to take energy out of the system. So to overcome the barrier here, the system has to fluctuate to the top of the barrier. Once it's at the top of the barrier, though, if it's very underdamped, in fact, in the limit that the system does not interact with the bath at all, it would then conserve energy. And provided it started with that amount of potential energy, it would undergo a periodic orbit, never actually committing down to the B basin. In the limit that it's coupled weakly to the bath, what might undergo that orbit and only very eventually lose enough energy to fall down the hole, fall down the well. So in a very underdamped limit, the limiting factor is not the ability to move spatially in Q, but rather for energy to diffuse away from this mode Q. So instead of thinking about a spatially diffusive limit, one could consider the so-called energy diffusion limit. To derive the transmission coefficient in this limit, we can go back to the original Langevin equation. That was mv dot is equal to minus gamma v, the force acting from that potential and a random noise. And instead of manipulating the Fokker-Planck equation in real space, we could write down a Fokker-Planck in energy. specifically Q dot. So what is the energy? The energy of the system in the underdamped limit has a velocity component. That's the kinetic energy. It also has a potential component. The joint equations of motion, instead of in Q and V, but rather in Q and E, can be solved for. Q dot, now as energy being a dynamical variable, is given by the difference in the energy less its potential. The equation of motion for the energy follows by just taking the derivative in time with respect to the energy, substituting in the equation of motion for V dot, and one gets 2 gamma E less omega of Q, plus now some new noise inherited from the equation of motion for V, whose statistics have to still obey a fluctuation dissipation theorem if this is the dissipative term, sorry, that's E dot. This is the drift, an effective drift term. Well, sorry, this is a whole diffusive term, no, dissipative term. Must mean that eta needs to depend on the value of the energy in order to balance that out correctly. So if I have these two equations of motion, the associated Fokker-Planck equation in Q and E I have a drift in the energy given by a partial derivative with respect to the energy, E less omega of Q. I have an energy dependent diffusion coefficient. And I have a deterministic drift in Q dots. Like so. There's no noise in the Q dot direction. All the noise is in the energy term. So this equation can be rewritten in a form, a derivative with respect to E gamma times a coefficient A of E, so-called action, times P of E and T. Essentially, we can eliminate Q completely if you actually worked out these expressions. You'd find that the Q pops out. And we have a diffusive piece, like so. All of this lies under that derivative. And now it must be that dE, that diffusion coefficient, again, has to balance out the distribution, has to be tuned such that the fluctuation dissipation relationship holds and ensures that a Boltzmann distribution is the steady state of the system. And the only way to ensure that is if D of E is equal to KBT gamma A of E. So now we have a form for an equation of motion for the energy, or the probability distribution of the energy, which is exactly the form that we have if we changed all the E's to Q's. This would look just like the Kramers theory we just worked out in the spatial diffusion limit. And in fact, we can immediately jump to the result of what the rate constant is. It is now proportional to KBT gamma. And now a nested integrals from minus infinity to EB, the barrier height that I have to overcome, the energy that I have to localize in the system to get to the top of the barrier, and a Boltzmann distribution, and an integral from E to infinity, dE prime, e to the beta E prime over this action. I'll inverse. So in the limit that the barrier is really large, so first, let's note that kappa is now proportional to gamma directly rather than 1 over gamma. This should make intuitive sense if what I'm waiting for is for the bath to take energy out of the system. The rate at which the bath does that is given by the friction. That's the dissipation rate from the bath. So now the rate limiting step is that energy flow, which is then proportional to gamma, which is very different than the spatial diffusion rate, where the rate limiting step was actually moving in space, which was proportional to 1 over gamma. So we find a very different sort of scaling behavior here. Maybe to draw some cartoons. So in the spatial diffusion limit, we get to the top of the barrier and then we undergo a random walk before eventually falling down. In the energy diffusion limit, we get to the top of the barrier and we have to wait for energy to come out of the system. So the recrossing along Q star in these two limits come from physically very different sorts of processes, either waiting for energy to leave the system or waiting for spatial motion to commit the system to the speed basin. Now, if the transmission coefficient, which embodies those dynamical corrections to the rate, initially goes proportional to gamma, but eventually goes inversely proportional to gamma, it must mean that there's a maximum in between. And indeed, this is the case. One can observe this in simple reactions by varying the viscosity of the solution, that you can transition between two different kinds of dynamical regimes. And this non-monotonic behavior of kappa is what's known as the Kramers turnover. So for completeness, let's quote the result for Kramers theory in this energy diffusion limit. In the limit that the barrier height is very high, those integrals can be simplified to some limit that EB is very high. All that will dominate this integral is the, let's see. So this action and the barrier height. So I will still have a Boltzmann probability to get to the top of the barrier in the limit that the barrier height is very high. I can do a saddle point approximation to those integrals and just evaluate the action at the top of the barrier multiplied by that probability to get to the top of the barrier. This is essentially saying that as the energy diffusion is related to that action as a function of energy, I just ask her what the value of the diffusion coefficient in energy is at the top of the barrier. Okay, so those are two canonical theories for understanding the dynamical corrections to transition state theory. And we find very different sorts of behaviors in the limit that the system couples very weakly to other additional modes. A rate limiting process could be the energy to leave that system. In the limit that the system couples really strongly to the bath, then that strong coupling reduces the spatial mobility of the system to cross the barrier, and thus the rate limiting step is just having enough persistent motion to commit. So both of these, while they operate in very different limits, are both only true when the bath relaxes quickly on the timescale of the motion of the reactive event. The theory that moves beyond that approximation, so includes non-Markovian effects in the estimate of the transmission coefficient, is known as Grota-Heinz theory. Excuse me. So if the bath relaxes on times similar to tau mole, which remember, we assume tau mole is quite small, then a non-Markovian theory for the dynamics at the top of the barrier may be necessary. So Grota and Heinz, Casey Heinz, worked out this theory in the 80s. They were largely thinking about things like photoisomerization or ion pair dissociation, things where there are maybe even electron transfer, things where there was a dynamics in a relevant reaction coordinate which was very fast relative to any slow reorganization of a surrounding solvent. So if we have a non-Markovian system, we know how to describe the dynamics of such. That's using a generalized Langevin equation. So let's, for concreteness, consider a parabolic barrier so Q double prime or Q double dot, the acceleration, let's set the mass to 1, is the frequency of that potential squared times Q. And our friction coefficient, time dependent, let's give the notation as C. And we have some random noise, which now has to satisfy the correlation function node 2, like so. Okay, so this is an integral differential equation. Looks kind of scary to solve, but we know how to do it. Oh, missed the Q dot. It is a friction after all. We know how to solve this kind of an equation. So if we're looking at motion at the top of this barrier, it's an integral differential equation, but the way we solve those, given it is linear in Q, it's just with Laplace transforms. So we can Laplace transform both sides. So remembering our Laplace transform primers, we've discussed, this admits a very simple way of writing down time derivatives. So a second order derivative produces two boundary values, two initial values in this case of Q at 0 and Q dot at 0. I have omega b squared, Laplace transform of Q on the right, and Laplace transform simplify convolution integrals, like what is introduced in this generalized Langevin equation, as now a product of Laplace transformed friction and the Laplace transformed Q. It's made a little bit more complicated by the fact that it's Q dot. And we have the Laplace transformed noise. So let's take this barrier as I've drawn it, centered at Q0. And let's assume that we start exactly at the top of the barrier. So that Q of 0 is equal to 0. We could rearrange this algebraic equation to solve for the Laplace transform of Q. This would give us a Q dot of 0, a Laplace transformed noise divided by, pick up s squared from the second derivative. I pick up an s times the Laplace transform of the friction, and minus omega b squared. Yep, okay, that checks out. All right, so Laplace transforms conserve sign. Now remember, to react, we're starting at the top of the barrier. Our transition state theory says we start at the top of the barrier, and we want to know at long times, what is the probability that we end up over on the right-hand side of the barrier, the reactant side of the barrier. So it is sufficient at long times to ask whether or not Q dot at 0 plus eta of S is greater than 0. Sorry. This is evaluated at some lambda, where lambda is the frequency associated with the fastest growing mode. So at long times, all I need to know is whether so if I start at the top of the barrier, the dynamics are unstable. So we only need to concern ourselves with a time scale associated with the quickest growing mode, the time scale that is going to act on the shortest time scales and commit me to that B basin. Because once I grow along that mode, the unstable dynamics will allow me to fall down the barrier quickly. So this frequency, often referred to as the Grota-Heinz frequency, is given by the solution of the equation lambda star plus lambda eta of lambda minus omega b squared. It's essentially asking for the root of this Laplace transform. So that root will give me the largest growing mode and dictate the commitment dynamics of this equation. If you think about inverting that Laplace transform, that's done through a contour integral. It will evaluate the complex exponential under that Laplace transform integral at the roots of the polynomial in the denominator. I need the root that will most quickly move Q along the positive direction. Turns out lambda is bounded by 1 from above, and by omega times the friction evaluated at 0 from below. That's a geometric argument from this equation. It follows that kappa, it can always be expressed as the flux at 0 times the probability that I get to B at time t. The equation of motion is determined by the likelihood that that initial velocity and the subsequent noise takes me over to B, divided by a way to write that initial transition coefficient, or the initial flux, the transition state theory estimate, would be to evaluate those at 0. A useful way to actually evaluate these integrals is to note that the step function has a Fourier transform representation. Like so, which actually follows from differentiating both sides and the usual Dirac delta function Fourier representation. Inserting that into kappa, that's in the numerator. This is in the denominator. Those averages are averages over the Gaussian distribution of the noise and the Maxwell-Boltzmann distribution of the initial velocities. As eta is a Gaussian random variable, this is just a usual Gaussian integral that we know how to do. It would yield the Fourier transform of e to the minus k squared over 2 beta minus 1/2 k squared, the variance of the noise evaluated at Grota Heinz frequency, divided by the Fourier transform of 1 over k. Oh, no, k's come out. The minus 2 over beta, k squared, where that, up to a factor of beta, is equal to the variance of the noise Laplace transformed which is then just 1 over lambda the friction evaluated at that lambda in Laplace space, which, when you do the final integrals, result in kappa being given by that fastest growing mode relative to the frequency at the top of the barrier. In the large friction limit, lambda naught is equal to omega of the barrier squared over the friction, the amplitude of the friction, so in the Markovian and large friction limit, which results in a kappa omega b over the friction, which is exactly what we got in Cramer's theory. However, in general, this Grota-Heinz estimate that depends on this ratio of the fastest growing frequency divided by the frequency of the barrier is going to be larger than the Cramer's theory estimate. Now, I've kind of washed over a lot of steps here, exactly showing why this is really the case, why this dictates the behavior at long times of the trajectory, how you actually do these Gaussian integrals. If that's confusing, fear not. It's in your homework for this next 2 weeks. The second problem, or the third problem, asks you to go through this calculation in detail, which is a good exercise in manipulating non-Markovian equations of motion. So the basic physics in this Grota-Heinz theory so I start at the top of the barrier, and I'm imagining that the barrier is really high, so that if I make my way very far to the right, I never come back. So there are absorbing states, essentially at plus and minus infinity in Q. And what I ask for are the specific actions of the bath, the specific time correlated values of noises that act on this particle at the top of the barrier that will commit me most quickly to the B basin. Because those dynamics are unstable, I can essentially, the Laplace transform that we worked out is essentially decomposing the trajectory that starts at Q is equal to 0 into growing exponentials that's what a Laplace transform does, is it decomposes a dynamical variable into exponential modes. And in Grota-Heinz theory, the mode that we care about is just the mode that grows the fastest, that most quickly brings me to a large value of Q such that I never expect to come back from. What that mode is not just determined by the bath itself. It's not just that the bath hits the particle in the right kind of way to commit it to the, it's not just that the bath without information from the system acts on the particle to commit it, but rather it has to do so with a characteristic frequency that is commensurate with the frequency of the barrier. I need to hit it with a resonance in such a way that I most quickly allow for the relaxation of the energy. That's really what this Grota-Heinz frequency is telling you, that it's the frequency with which, given the ability of the bath to act, as characterized by its memory kernel, and the frequency over which motion occurs. Again, if I start at the top of the barrier without any coupling to the bath, I would undergo a periodic motion. So that period, there's a resonance condition with that period, and the period that the bath can act through its memory, that will most quickly bring me down in energy. And that's what that lambda is telling you. Okay, so those are somewhat complicated dynamics. Sorry about this. But are models for going beyond just transition state theory. So in the next couple lectures, with these kind of models in hand, we'll do a couple things. First, we'll apply this understanding of rare events to a canonical problem in chemical dynamics, electron transfer, and work out Marcus's theory of electron transfer. And then we will generalize this a little bit to bimolecular processes, and further to think about what is really missing in this whole picture. We've slaved ourselves in talking about reaction kinetics to this reaction coordinate. We've projected down what are complex dynamics in a high dimensional space onto 1 degree of freedom. In general, that's very hard to know what the relevant degree of freedom is that would make that projection most faithful. And so thinking about ways of generalizing notions of transition states to high dimensional systems will bring us into a discussion of transition state ensembles. So the distribution of configurations that are least decided in terms of whether or not they react, which are slices along a path ensemble, an ensemble condition on reacting. So there are contemporary perspectives on reaction rate theory using path ensembles. There are numerical means for generating reactive events in a computationally expedient way using transition path sampling. So we'll talk about those sorts of things in the last lecture on this series. And so look forward to that. I guess we can cut out a minute or two early. I hope you all are well, and I'll look forward to talking to you all in the small group sessions. One quick note while I'm thinking about it, if you have not already committed to a project for this class, or have not had a project okayed by me yet, please do get in touch soon. I am hoping that most of you take at least this month to work on the project. It will be due at the end of the semester and the end of RRR week. And so I hope you all are actively working on those. So reach out if you've not decided on a project or are lost and need some guidance.